Of every galaxy humanity has ever photographed, every spiral and elliptical caught by Hubble, every faint smudge sharpened by James Webb, every pinprick of ancient light in the deep field posters that hang on the walls of planetariums, roughly 97% are already permanently beyond our reach. Not difficult to reach, not technologically challenging to reach, impossible to reach. The number is not a guess. It comes from a paper published in 2007 by two physicists at Case Western Reserve University, Lawrence Krauss and Robert Scherer, who set out to calculate how far a future humanity could in principle ever travel, and were forced by their own math to draw a line that turned out to be small. Their calculation was simple. Their conclusion was devastating. The universe is expanding faster than light can cross the gap, and the gap is widening every second that passes. Even if we built a spacecraft tomorrow that could travel at 99.99% of the speed of light, it would never catch them. The galaxies we see in those deep field images, the spirals and ellipticals captured by the James Webb Space Telescope, the faint smudges that fill the dark patches of the sky, are already ghosts. We are looking at light that left them billions of years ago when they were still close enough to be part of our story. They have since slipped away. The universe has been quietly closing doors behind us our entire existence, and the doors are slamming faster every year. Tonight, we are going to ask the question that science fiction has avoided for 100 years. Not whether humanity could spread to the stars, but how far we could spread before the universe itself stops us. We are going to discover that there is a wall waiting for us out there, a wall made not of matter but of space itself. A wall that is moving away from us at the speed of light. A wall that defines the absolute maximum size of any civilization that humanity will ever build. And by the end, you will understand that the future humans have always imagined a species that fills the galaxy, then the local group, then perhaps the supercluster, is mathematically impossible. Not because of energy, not because of fuel, because the universe is built to keep us small. If you enjoy these nighttime science journeys, take a moment to like and subscribe. It genuinely helps the channel grow and allows us to keep making these long-form explorations of the cosmos for you. Get comfortable. We are about to find the edge of everything humanity will ever touch. Let us begin. When you imagine a future for humanity, you almost certainly imagine it bigger than this. You imagine cities on Mars, settlements on the moons of Jupiter, mining colonies in the asteroid belt. You imagine generation ships crossing the dark between stars, arriving at Proxima Centauri, terraforming new worlds, building a galactic civilization that spans the Milky Way. This is the dream that has driven science fiction since Jules Verne first wrote about a journey to the moon. And it is the implicit assumption behind almost every modern conversation about the long-term future of our species. Humanity does not stay on Earth. Humanity expands. The only question is when and how. The numbers tell a different story. Let us begin where the dream usually begins, with the nearest star. Proxima Centauri sits at a distance of approximately 4.24 light-years from our Sun. That is the closest stellar neighbor we have. Every other star, every other potential destination is farther. To put that number into something a human mind can hold on to, consider this. The Voyager 1 spacecraft, launched in 1977, is the fastest human-made object ever to leave the solar system. It is traveling at roughly 61,000 kilometers per hour. After 47 years of continuous flight, it has covered about 24.6 billion kilometers. That sounds like an enormous distance. It is. No human creation has ever traveled farther. But at its current speed, if Voyager 1 were aimed directly at Proxima Centauri, it would arrive in approximately 73,000 years. 73,000 years. That is longer than the entirety of recorded human civilization, longer than the cave paintings at Lascaux have existed, longer than the genetic split between modern humans and Neanderthals, and it would arrive at one star. 1. The galaxy contains an estimated 250 billion of them. Now, the obvious response is that we will go faster. We will not be limited to Voyager speeds forever. Imagine a future propulsion system, a fusion drive, an antimatter engine, a beamed energy sail that can push a probe to 10% of the speed of light. At that velocity, Proxima Centauri becomes a 42-year journey, a human lifetime. Maybe 2 if you account for acceleration and deceleration. The galaxy starts to feel reachable. Push the technology further. Imagine 50% of the speed of light. Now the nearest star is less than 9 years away. The most distant stars in the Milky Way are 100,000 light-years away. But at that speed, you cross them in 200,000 years. That is shorter than the time our species has existed. The galaxy starts to feel like a continent rather than an ocean. And if you accept the equations of special relativity, the picture gets even more dramatic. At speeds approaching the speed of light, time slows down for the traveler. A crew aboard a ship moving at 99.99% of light speed could, in their own subjective experience, cross the entire Milky Way in a single human lifetime. They would arrive at the far side of the galaxy as middle-aged adults. Earth, of course, would be 100,000 years older, but the universe itself, would still be there waiting. The galaxy would still exist. Their destination would still be reachable. This is the optimistic case. This is what every honest physicist will tell you is theoretically possible within the known laws of physics. There is no rule that says you cannot travel at 99.99% of the speed of light. The energy requirements are absurd. The engineering challenges are beyond anything we currently know how to build. But the laws of nature do not forbid it. They simply make it expensive. So the galaxy, all 100,000 light-years of it, is in principle within humanity's reach. Difficult, yes. Expensive beyond imagining, yes. But possible. And here's where the story turns. Because the galaxy is not the universe. The galaxy is one small structure in a cosmos that contains an estimated 2 trillion others. And when you try to leave the Milky Way, when you try to cross the gap between galaxies, something happens that no amount of engineering can solve. The space between galaxies is not stationary. It is expanding. And it is expanding faster than you can travel through it. To understand why this is the central fact that determines the maximum size of any human civilization, we have to go back to 1929. To a man named Edwin Hubble standing at the eyepiece of the 100-inch Hooker telescope at Mount Wilson Observatory in California. Hubble was doing tedious work. He was measuring the distances to galaxies. Not pretty work, not glamorous work, just careful, painstaking observation night after night. And he was also measuring something else. The redshift of those galaxies. When a galaxy moves away from you, its light is stretched to longer wavelengths, shifted toward the red end of the spectrum. The faster the recession, the greater the redshift. Hubble was doing both measurements at once, the distance to the galaxy and the speed at which it was moving away. And when he plotted his data, he saw something that should not have been there. A pattern. A straight line. Galaxies that were twice as far away were receding twice as fast. Galaxies 3 times farther away were receding 3 times as fast. The relationship was clean. Distance and recession velocity were directly proportional. There was only one interpretation that made physical sense. The universe was not static. It was expanding. Not expanding in the sense that galaxies were flying outward through pre-existing space, like fragments from an explosion. Expanding in the sense that space itself was getting larger. Every galaxy was moving away from every other galaxy because the distance between them was growing. There was no center to this expansion. From any galaxy in the universe, you would see exactly the same thing. Everything around you receding. Everything beyond your local neighborhood pulling away. This was, at the time, the most disorienting discovery in the history of physics. The universe was not eternal. It was not unchanging. It was alive in some deep mechanical sense, growing, stretching, transforming itself moment by moment. And if you ran the expansion backward in time, all of those galaxies converged. They had to. Go far enough into the past, and the entire observable universe was concentrated in a single point of unimaginable density and temperature. The Big Bang, the beginning of everything we can measure. That was 13.8 billion years ago, and the universe has been expanding ever since. For most of the 20th century, cosmologists assumed that the expansion would slow down over time. The reasoning was straightforward. Gravity is an attractive force. All the matter in the universe pulls on all the other matter. So even though the universe was flying apart from its hot, dense beginning, gravity should have been gradually putting on the brakes. The question that consumed cosmology for decades was not whether expansion was slowing. That was assumed. The question was whether gravity would eventually win. If there was enough matter in the universe, gravity would eventually stop the expansion and pull everything back together into a final collapse. The Big Crunch. The universe ending in the reverse of how it began. If there was not enough matter, the expansion would continue forever, but at a steadily decreasing rate, approaching but never quite reaching a halt. The universe would coast outward, getting slower and slower, but never stopping. Both possibilities were sobering. Both involved a universe that was, in some fundamental sense, calming down, settling, approaching equilibrium. Then, in 1998, two independent teams of astronomers shattered that picture. They were studying Type Ia supernovae, exploding white dwarf stars that all reach roughly the same peak brightness because they all detonate at the same critical mass. Because of this consistency, Type Ia supernovae make excellent distance markers. Measure how bright one appears in the sky, compare it to how bright it actually is, and you can calculate exactly how far away it is. The two teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using these supernovae to measure the expansion history of the universe. They wanted to know how much expansion had slowed down over cosmic time. They expected to find a clear deceleration. What they found instead changed cosmology forever. The distant supernovae were fainter than expected. Not by much, but by a statistically significant amount. Fainter means farther away than they should have been if the expansion had been slowing down. There was only one explanation that fit the data. The expansion of the universe was not slowing, it was accelerating. Some force was pushing space apart, overcoming the gravitational pull of all the matter in the cosmos, and making the rate of expansion increase over time. The discovery would later win the Nobel Prize in Physics in 2011, and it created a problem that we are still trying to solve. What was causing the acceleration? What was pushing space apart? The answer, or the placeholder for the answer, is dark energy. We do not know what it is. We have known about its existence for less than 3 decades, and in that time it has resisted every attempt to identify it. The simplest hypothesis is that empty space itself has an inherent energy, a property of the vacuum written into the fabric of reality that pushes outward with a small but persistent force. As the universe expands and more space comes into existence, more of this vacuum energy comes with it, and the outward push grows stronger. It is a feedback loop. More space means more dark energy. More dark energy means faster expansion. Faster expansion means even more space appearing. The universe is, in a real sense, pumping itself full of repulsive force, accelerating its own growth. And here is the part that matters for humanity's future. Dark energy makes up approximately 68% of the total energy content of the universe. Dark matter, invisible and equally mysterious, makes up another 27%. Ordinary matter, the stuff that builds stars and planets and atoms and human beings, makes up only about 5% of the total. The accelerating expansion of space is by far the dominant force shaping the large-scale structure of the cosmos. And it is winning. It has been winning for approximately 5 billion years. It will keep winning for as long as the universe exists. Every second that passes, the acceleration creates a little more space between galaxies, and that space contains a little more dark energy, and the acceleration grows slightly stronger. The process is exponential. The universe is not just expanding, it is running away from itself faster and faster, and there is nothing that can stop it. This has a consequence that most people, even most science enthusiasts, have never fully reckoned with. It means there is a wall out there, a wall in space-time, a wall that no civilization, no matter how advanced, can ever cross. Astronomers call it the cosmological event horizon, and it is the most important boundary that humanity will ever encounter. To understand the cosmological event horizon, you have to first understand a strange consequence of the expansion. As space expands, distant galaxies appear to be receding from us. The farther away they are, the faster they recede. This is Hubble's law, and it has been confirmed thousands of times over, with thousands of independent measurements. The current value of the Hubble constant, the rate of expansion, is approximately 70 kilometers per second per megaparsec. A megaparsec is 3.26 million light-years. So for every 3.26 million light-years of distance between 2 points in space, The space between them is growing at 70 kilometers per second. A galaxy 10 megaparsecs away is moving away from us at 700 kilometers per second. A galaxy 100 megaparsecs away is moving away at 7,000 kilometers per second. A galaxy 1,000 megaparsecs away is moving away at 70,000 kilometers per second. And here is the critical step. If you go far enough out, the recession velocity reaches the speed of light. At a distance of approximately 300 megaparsecs, about 14 billion light-years, the space between us and that distant galaxy is expanding at 300,000 kilometers per second, light speed. Beyond that distance, the recession velocity exceeds light speed. The galaxies out there are not moving through space faster than light. That is forbidden by relativity. What is happening is something stranger. The space itself between us and them is expanding faster than light can cross it. Relativity has no problem with this. The cosmic speed limit applies to objects moving through space, not to space itself. Space can expand at any rate it likes. And dark energy ensures that beyond a certain distance, it does. Now think about what this means for a photon. A photon of light leaves a distant galaxy and starts traveling toward us at the speed of light. It is doing exactly what photons do, moving as fast as anything can possibly move. But the space it is traveling through is expanding. And if that expansion is faster than the photon can swim against it, the photon never arrives. The distance between the photon and us actually grows over time because the expansion is winning. The photon is like a swimmer caught in a current stronger than they can swim. They are moving forward through the water, but the water is carrying them backward faster. They never reach the shore. Every galaxy beyond that critical distance is, right now, emitting light that will never reach us. Never. Not in a million years. Not in a billion years. Not in the entire infinite future of the universe. The light is leaving the galaxy. It is heading in our direction. It is moving at the speed of light. And it will never get here. Those galaxies have crossed our cosmological event horizon. They are causally disconnected from us. We cannot see their present. We cannot signal them. We cannot reach them. We cannot in any way influence what happens there or be influenced by what happens here. They might as well be in a different universe. And here is the cruelty of the geometry. The horizon is not static. It is shrinking. As dark energy continues to accelerate the expansion, more and more distant galaxies are being pushed across the line. Every year, a small number of galaxies that were until recently still potentially reachable cross the event horizon and become permanently disconnected from us. The observable universe, which currently contains about 2 trillion galaxies, will contain fewer galaxies in the future, not because they are disappearing, but because they are being carried beyond the wall by the expansion of space. Right now, this very moment, somewhere out at the edge of our cosmic neighborhood, the light from a galaxy is taking its final journey across the dwindling gap. After this moment, no further light from that galaxy will ever reach us. The galaxy continues to exist. Stars are being born there. Planets are forming there. If life exists there, it is continuing to exist there. But for us, it has ended. It has slipped past the horizon, and no signal from it will ever cross the void again. Multiply that across the entire sky. Multiply it across all the galaxies we can currently see. Run the clock forward. The cosmological event horizon contracts inward like a closing iris, slowly, inexorably, year after year. Trillions of galaxies disappear from our reach. Then billions. Then millions. Then thousands. Until eventually, on a long enough timescale, only one structure remains. Our home. The local group. The local group is the small collection of about 80 galaxies that are gravitationally bound to the Milky Way. It includes our galaxy, the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies orbiting them. The total span of the local group is approximately 10 million light-years. That sounds enormous. By human standards, it is. But the observable universe is 93 billion light-years across. The local group is a vanishingly small fraction of that, less than 1/10,000th of 1% of the volume of space we can currently see. And here is the thing that will matter most for the rest of this documentary. The local group is bound. It is held together by gravity. Gravity inside the local group is stronger than the dark energy trying to pull it apart, so the local group will survive. While the rest of the universe stretches and disperses and accelerates beyond the horizon, the local group will remain intact. The Milky Way and Andromeda will collide in roughly 4.5 billion years, merging into a single elliptical galaxy that astronomers have already nicknamed Milkomeda. Over time, the smaller dwarf galaxies will fall in and be absorbed. The local group will compact down into a single enormous merged galaxy, surrounded by absolute emptiness in every direction. That merged galaxy is the largest structure that any civilization originating on Earth could ever, even in principle, hope to occupy. Not the Milky Way, the merged remnant of our entire local group. After that, the wall closes. There is nothing beyond it that we can reach. There is no point in even trying. Now let us be precise about the numbers, because this is where the dream of a galactic empire meets the cold geometry of the cosmos and breaks. The future visibility limit, the boundary of what could in principle be reached by a beam of light leaving Earth today, lies at a distance of approximately 16 billion light-years. Anything within that distance can still be touched. Anything beyond it cannot. That is a sphere about 32 billion light-years across. It sounds large, but that is the limit of light, not the limit of physical travel. A spacecraft traveling at any speed slower than light, which is to say any actual spacecraft that could ever exist, is even more limited. The reachable universe for a sublight-speed civilization is a smaller sphere within the light cone, and as you slow down, that sphere shrinks dramatically. In 2014, the astronomer Toby Ord, working at Oxford, did the calculation in detail. He asked a simple question. If humanity launched a colonization wave tomorrow, what fraction of the observable universe could we ever, in principle, settle? Assuming we could travel at any sublight speed we wanted, with technology that we cannot even currently imagine, what is the upper limit? The answer was crushing. Approximately 4% of the volume of the currently observable universe is in principle reachable from Earth. The remaining 96% is already gone, already across the horizon or moving toward it faster than we could ever catch them. And that 4% assumes near-light speed travel from today, with infinite energy budgets and no internal obstacles. The realistic number, accounting for the actual physics of travel and the time needed to develop civilization at each destination, is far smaller. The reachable universe is more like 1/10% of what we can see. And even that estimate is optimistic, because the calculation assumes we start expanding outward today. Every century we delay, the reachable volume shrinks. Every millennium that humanity remains on Earth, or in its local neighborhood, more galaxies slip beyond the wall. There is a clock ticking, and it has been ticking for billions of years before we existed. It will keep ticking long after we are gone. So when we imagine humanity spreading across the cosmos, what we are actually imagining is humanity claiming a sliver of what is currently visible, then watching the rest fade away. Even the most successful expansionist civilization in the history of the universe is constrained to a tiny, gravitationally bound island in an ocean that is rapidly emptying. The galaxy is reachable. The local group is reachable, with enormous effort. The Virgo supercluster, our home supercluster of about 100,000 galaxies, might be partially reachable if we leave very, very soon. Anything beyond it is already lost. And the further we move beyond the local group, the more sharply the wall closes in. Every galaxy outside the local group is being carried away from us. Some quickly, some slowly, but all of them are moving in the same direction, away. And the acceleration ensures that the velocity of their flight grows with every passing year. There is something almost unbearable about this picture once you fully absorb it. The night sky we look up at contains the light of galaxies that are, even now, racing away from us at speeds that mean we will never reach them. We are looking at the past of structures that are already in the present, beyond our cosmic touch. The light we see from Andromeda is 2.5 million years old, but Andromeda is still bound to us. The light we see from the Virgo cluster is 54 million years old, and Virgo is loosely bound to us. gradually slipping. The light we see from the Coma cluster is 320 million years old, and Coma is already lost. The light we see from the most distant galaxies imaged by James Webb is over 13 billion years old, and those galaxies, if they still exist as galaxies at all, are so far beyond our reach that they have effectively ceased to be part of our universe. The vast majority of the cosmos is, from the perspective of any civilization, a museum, a collection of ancient images preserved in light. We can look at them, we can study them, we can build whole sciences around them. We cannot go to them, we cannot send a probe to them, we cannot send a message to them. They are forever just photographs. Beautiful, scientifically priceless and unreachable. This is the wall. This is what the universe has built around us. Not a wall of matter that we might one day learn to break through. A wall of space itself, expanding faster than any conceivable engine could overcome. The most fundamental, the most absolute boundary that physics permits. And every civilization that has ever arisen in the cosmos, on any planet, around any star, has been confined behind a similar wall, each one limited to its own local gravitationally bound region, each one isolated from every other by an expanding ocean of nothing. Now you might be thinking that this is a problem only for the very long term. That for now, for the next billion years or so, the local group and even some nearby clusters are all in front of us, technically reachable, technically open. That this is a future problem, not a present one. That is partly true. But the closing of the wall has already begun, and the speed at which it is closing is something most people deeply underestimate. Because the cosmological event horizon is not the only wall, it is just the largest. There are other limits, closer and tighter, that constrain how far any civilization can spread. And the first of those limits is the simplest. It is the limit on how fast you can move at all. Special relativity tells us that nothing carrying information or mass can travel faster than the speed of light. Approximately 299,792 kilometers per second. This is not a technological limit. It is not a problem we will eventually engineer our way past. It is built into the geometry of space-time itself. The faster you go, the more energy it takes to go faster. As you approach the speed of light, the energy required to gain even a tiny additional fraction of velocity grows toward infinity. To actually reach light speed, you would need infinite energy. There is no escape clause. There is no workaround. There is no advanced technology that physics permits to break this rule. Every theoretical concept that has ever been proposed for getting around it, wormholes, Alcubierre warp drives, hyperspace tunneling, all of them require exotic forms of matter and energy that may not exist in the universe at all, and that even if they do exist, would require resources on scales that no civilization could plausibly assemble. So for the purposes of any realistic discussion of expansion, the speed of light is the cap. It is the upper limit on how fast you can travel, how fast you can communicate, and how fast you can extend your civilization outward. And what this means in practical terms is that every act of expansion is also an act of fragmentation. The moment a human civilization sends a colony ship to a star 10 light-years away, that colony is at least 10 years out of communication. By the time a message from Earth reaches them, 10 years have passed. By the time their response arrives, 20 years have passed since the original message was sent. The two communities, Mother World and Colony, are operating on different timelines. They are not really one civilization anymore. They are two civilizations connected by a slow trickle of decades-old information. Extend that to 100 light-years, and the lag becomes generational. A child born on a colony world 100 light-years from Earth will live their entire life and die before any message they sent as a young adult could possibly be answered by Earth. Their colony will have its own politics, its own culture, its own science, its own questions, evolving independently for centuries before any influence from the home world can arrive. Extend the distance to 1,000 light-years, 10,000 light-years, the entire breadth of the galaxy, and the concept of a single human civilization becomes meaningless. There can be human worlds. There cannot be human empires. The light barrier ensures that any sufficiently spread out civilization decomposes into a constellation of independent islands, each one effectively isolated from all the others by the very speed of light that defines causality. So even within our local group, even within the reachable region, the universe imposes a kind of mandatory loneliness. You can spread, but spreading means breaking apart. You can occupy more space, but occupying more space means losing coherence. There is no version of cosmic expansion that preserves a unified civilization across vast distances. Every star system you settle becomes, on a long enough timeline, its own world, with its own history, its own destiny. And this is before we even consider the second wall, because the cosmological event horizon and the speed of light limit are only two of the constraints that the universe imposes on any expanding species. There is also time. Time, in deep cosmological terms, is running out. Not for the universe as a whole. The universe will continue to exist for trillions of years yet, probably much longer. But for the conditions that allow civilization to exist. For the era in which stars burn and planets form and complex chemistry can happen, the window is finite. We live inside what cosmologists call the stelliferous era, the age of stars. It began about 100 million years after the Big Bang when the first stars ignited, and it will continue for approximately 100 trillion years more until the last red dwarf burns out and the sky goes dark. That sounds like an immense amount of time, and it is. But humanity is not free to use all of it, because the conditions for life are not stable across that entire stretch. They change, they evolve, and they grow less hospitable as time passes. The early universe, the universe of the first few billion years, was hot and chaotic. Stars formed quickly, often massively, and died violently. Heavy elements were scarce. The conditions for stable, long-lived planets capable of hosting complex life were narrower. The late universe, the universe of the next 100 trillion years, will be cold and dim. Star formation will slow as the available gas is consumed or scattered by expansion. Galaxies will gradually exhaust their reserves. The lights will go out, one by one. The reachable region of the cosmos is not just shrinking in volume. It is shrinking in available time and available resources, and every civilization that ever arises within it must contend with a deadline, a point at which the conditions that gave rise to them will no longer hold. Imagine a civilization that arises 10 trillion years from now in a universe that has already largely cooled. Most stars are gone. The galaxies they can see are isolated, ancient, dim. The local environment is sparse. Such a civilization, even if it possessed every technology we can imagine, would find the universe vastly less hospitable than the one we inhabit. They would have less raw material to work with, fewer stars to harvest, less time before everything ran down. We are not in the middle of the cosmic story. We are very, very near the beginning. And one of the strange and unsettling consequences of this is that humanity, on cosmic timescales, has been born early, almost suspiciously early. Some cosmologists have pointed out that if you ask which kinds of stars are most common in the universe, the answer is small red dwarfs. They make up roughly 75% of all stars in the Milky Way. They burn slowly, conservatively for trillions of years. A planet orbiting a red dwarf could host life for vastly longer than a planet orbiting a sun-like star. If life were going to arise around any random star in the universe, the most probable star would be a red dwarf. And the most probable time would be tens or hundreds of billions of years from now, deep into the future, long after stars like our sun have died. Instead, here we are, orbiting a yellow dwarf. In the first 14 billion years of cosmic history, less than 0.1% of the way through the era in which life is possible. We are early in a way that is mathematically surprising. And the question that follows from this is uncomfortable. If we are this early, what does that mean for our future? One possibility is that we are simply lucky, an outlier, a species that happens to have arisen near the beginning of the great cosmic story. Another possibility is more troubling. The other possibility is that intelligent civilizations tend not to survive very long, that something filters them out. That the reason we are so early is that no civilization arising later has yet had the chance to look back and notice that they are late. The longer a civilization survives, the more space it tends to fill. If civilizations routinely lasted for millions or billions of years, they would inevitably spread out and become visible from enormous distances. They would build structures that we could detect. They would broadcast signals that we could intercept. They would leave footprints in the chemistry of stars they harvested for energy. We have searched for these signatures for decades. We have not found them. This is the silence that haunts modern astronomy. The Fermi paradox, named after the physicist Enrico Fermi, who in 1950 asked the simple question, "Where is everybody?" The galaxy has been around for 10 billion years. Even if interstellar travel proceeds slowly, even at 1/100th of the speed of light, a single ambitious civilization could, in principle, colonize the entire Milky Way in roughly 10 million years. That is a blink of cosmic time. There has been more than enough time for many such waves of colonization to sweep through the galaxy many times over. The galaxy should be full, visible, loud. Instead, it is quiet, empty, apparently untouched. There are many possible explanations for this silence, and we have explored them in previous documentaries. But one of the most haunting explanations is also the most relevant to our current question. Civilizations may not spread very far, because they cannot spread very far. Because the universe itself is built to keep them contained. The walls of light speed, of the cosmological event horizon, of the resource limits within a single solar system, of the difficulty of surviving across the centuries it takes to travel between stars, all of these conspire to prevent any civilization from filling more than a tiny fraction of its allotted space. The galaxy may be quiet, because every civilization that ever arose was, like us, trapped behind walls it could not breach, limited to a few neighboring stars, a few orbiting outposts, before time or distance or entropy ended the experiment. If that is the case, then humanity's future is not the galactic empire of science fiction. It is something far smaller, far more local, and far more precious. It is a brief flowering of consciousness on one branch of one filament of one tiny corner of an enormous, dispersing, increasingly empty cosmos. And the question we should be asking is not how big we will become. The question is how much we can do before the walls finish closing. So let us count the stars. Let us count the literal number of destinations available to a civilization that begins on Earth and tries, with maximum effort and maximum ambition, to claim as much of the universe as it physically can. Let us start with our nearest neighborhood and work outward, watching the numbers grow at first, then plateau, then collapse against the walls we have just described. Within 10 light-years of Earth, there are approximately a dozen stars. Most of them are small, dim red dwarfs, with planetary systems that have been studied only minimally. Some of them host confirmed exoplanets. Proxima Centauri b orbits the closest star to our Sun and may be roughly Earth-sized, though its habitability is disputed. TRAPPIST-1, about 41 light-years away, hosts a remarkable system of 7 roughly Earth-sized planets, several in the habitable zone. Tau Ceti, 11.9 light-years away, is a Sun-like star that may host multiple planets. These are the destinations that humanity, with sufficient ambition and centuries of effort, could in principle reach within a single human civilizational lifespan. A handful of worlds, a few stellar systems, the first foothold beyond the cradle. Expand the radius to 100 light-years and the number grows to roughly 15,000 stars. This is the volume of space that our radio signals have already passed through. Anyone listening for us within 100 light-years has had the opportunity to hear the leakage of our electromagnetic civilization. Earth has been broadcasting since the early 20th century, and that bubble of human noise has been expanding outward at the speed of light. It is now about 125 light-years in radius. 15,000 stars is a lot of potential destinations. With near light-speed travel, all of them could in principle be reached within a few centuries of any colonization wave. Push the radius to 1,000 light-years, and the number climbs to roughly tens of millions of stars. Within 10,000 light-years, you have access to a significant fraction of the Milky Way, perhaps tens of billions of stars. By the time you have spread across the full 100,000 light-year span of the galaxy, you have access to all 250 billion of them. This is the maximum reach of a single galactic civilization. Even at near light speed, it would take at minimum 100,000 years to send a signal from one edge of the galaxy to the other. And the practical timeline for actual physical colonization, even with optimistic assumptions about travel speed and the establishment of new outposts at each star, would likely stretch into millions of years. But it is, in principle, possible. The galaxy is within reach. The galaxy is the maximum size of a humanly contiguous civilization. Beyond that, you start to encounter the local group, which adds a few 100 billion stars across roughly 80 galaxies over a span of 10 million light-years. Reaching the galaxies of the local group would require crossing the intergalactic gulf, vast empty stretches of space between island universes. The gap from the Milky Way to Andromeda is 2.5 million light-years of essentially nothing: no fuel stations, no way stations, no civilizations to trade with along the way, just vacuum. Crossing it requires a ship that can sustain itself for the entire duration of a 2.5 million-year voyage, or compress that time through near light-speed travel and accept that the crew arriving will be unimaginably distant from anything that resembled Earth. It can be done. Physics permits it. Engineering does not currently know how to do it, but the laws of nature do not forbid it. So the local group is, in principle, accessible. And once you have reached the local group, you have reached the maximum size of any gravitationally bound civilization. Beyond that, you hit the wall. The expansion of space starts to exceed the practical reach of any sublight-speed vessel. Every galaxy beyond the local group is being pushed away faster than you can chase it. So let us put a final number on this. The maximum theoretically reachable region for a civilization originating on Earth, assuming we expand outward at near light speed starting now, contains approximately 10 quadrillion stars. That is the upper bound. That is the absolute ceiling, the sphere that includes our local group, the Virgo supercluster if we move fast enough, and a few neighboring clusters if we are extraordinarily efficient. 10 quadrillion stars, give or take an order of magnitude. It sounds enormous. It is enormous by any human standard. But the observable universe contains approximately 200 sextillion stars, 2 followed by 23 zeros. Our maximum reach is therefore roughly 1 star in every 20 million that we can see. We can settle at most 1 out of every 20 million stars that fall within our telescopes. The other 99.999995% of them are gone, already past the horizon, already drifting beyond our reach, already part of someone else's sky, if anyone is there at all. And here is the calculation that puts the rest of this conversation into perspective. The reachable universe has been shrinking for billions of years. Every second that passes, more galaxies cross the cosmological event horizon and leave humanity's potential reach forever. If we had begun colonization a billion years ago, our reachable region would have been larger. If we wait another billion years, it will be smaller still. The clock has been running since long before our species existed. It will keep running long after we are gone. And the more we delay, the less there is to claim. There is a curious mathematical wrinkle here that deserves attention. The cosmological event horizon is not located at the same distance for everyone. It is a personal horizon. Every observer in the universe has their own. From our perspective on Earth, certain galaxies are reachable. From the perspective of a hypothetical observer in the Andromeda galaxy, a slightly different set of galaxies is reachable. The horizons overlap but do not coincide. This means that even if humanity were to spread across the entire local group, different parts of the resulting civilization would have access to slightly different cosmic neighborhoods. A colony on the far side of Andromeda could, in principle, reach a few galaxies that are unreachable from Earth. But not many. The total reachable region for any civilization originating in our local group is essentially the same regardless of which planet within the local group you start from. The walls are functionally the same. So humanity does not gain meaningful new territory by spreading first. Spreading does not unlock new horizons. It only fills in the territory already enclosed by the wall that surrounds our home. There is one strategy that could, in theory, extend our reach significantly. It involves a concept that has fascinated thinkers since John von Neumann first formalized it in the 1940s: the self-replicating probe. The idea is straightforward. Build a single robotic spacecraft capable of crossing the gap between stars, landing on a planet or asteroid in another system, gathering raw materials, and constructing copies of itself. Each copy then launches toward additional star systems, where they too gather resources and build more copies. Within a few generations of replication, you have an exponentially growing fleet of probes spreading outward through the galaxy. At even modest speeds, perhaps 10% of light speed, this kind of expansion could cover the entire Milky Way in approximately 10 million years. The galaxy could be filled with our machines or our distant biological descendants in a time that is short compared to the age of the galaxy itself. The von Neumann probe is the most efficient possible mechanism for cosmic expansion. It does not require maintaining a unified civilization. It does not require constant communication. It does not require enormous shipments of personnel or supplies from a home base. Each probe is self-sufficient. Each generation of probes operates independently. The expansion happens automatically, exponentially, without ongoing intervention from the originating species. If humanity built such probes today and launched them outward, our reach could in principle extend across the entire local group and into the nearer parts of the Virgo supercluster. The probes could continue replicating and spreading for millions of years after the originating species had died out. They would be a kind of cosmic inheritance, a legacy of expansion that outlives its creator. But even self-replicating probes hit the wall. They can spread through gravitationally bound structures, but they cannot cross the cosmological event horizon any more than a living crew can. The expansion of space is impartial. It pushes machines and biology away at the same rate. The probes can fill the local group, they cannot fill the universe. And there is another consideration that should give us pause. If self-replicating probes are possible, and if any civilization has ever existed in the universe long enough to build them, then the galaxy should already be filled with the probes of someone else. Some earlier species, somewhere in the Milky Way, somewhere in the local group, should already have unleashed such a wave. We should see evidence of it. We should find traces of alien machinery in our solar system, on our moon, in the asteroid belt, in the atmospheres of nearby planets. We have not. Every survey we have conducted has come up empty. Either we are the first civilization in our reachable region capable of such a project, or every civilization that has tried has failed. Or there are limits we do not yet understand that prevent the strategy from working as cleanly as the mathematics suggests. Whatever the explanation, the silence places a constraint on what is plausible. And it raises the possibility that the upper limit on humanity's expansion is not just defined by physics. It may also be defined by something darker, something built into the nature of civilization itself, that ensures no species spreads as far as it theoretically could. Let us return to physics, though. Let us assume the optimistic case. Assume humanity does build the probes. Assume we do begin to spread. Assume we manage, somehow, to occupy a significant fraction of the local group within the next few million years. What does that future look like? It looks isolated. Profoundly isolated. The colonies in different galaxies would have no realistic communication with each other. A message from the Milky Way to a colony in the Andromeda galaxy takes 2.5 million years to arrive. A response takes another 2.5 million years. The two civilizations are effectively independent. They share an origin, but they share nothing else. They cannot influence each other on any meaningful timescale. They cannot trade, they cannot coordinate, they cannot help each other in any way that matters. The dream of a unified interstellar civilization survives only at the scale of a single solar system, or at most a tight cluster of a few neighboring stars. Beyond that, every settlement becomes its own world. And the colonies themselves would face progressively grimmer cosmic conditions. The galaxies of the local group are not eternal. The Milky Way and Andromeda will merge in 4.5 billion years, and the resulting collision will reshape the gravitational landscape of every star system within. Many planets will be ejected from their orbits. Many star systems will be flung into intergalactic space. Some will fall toward the central black hole of the merged galaxy. The colonies that survive that merger will inhabit a transformed environment, one that has been violently rearranged by the gravitational consequences of two giant galaxies colliding. After the merger, the merged galaxy, Milkomeda, will continue to evolve. Star formation will gradually decline as the available gas is consumed. The remaining gas in the local group will be slowly depleted. New stars will be born less and less frequently. By the time 100 trillion years have passed, all of the small red dwarfs that have been holding out will finally exhaust their fuel and die. The stelliferous era will end. The sky will go dark. The colonies that survive long enough to witness this will look up at a night sky that contains no other stars. Only black holes and the cooling embers of dead stellar remnants. They will not be able to see other galaxies, because all of them will have long since slipped beyond the cosmological event horizon. They will be alone in a way that no human civilization has ever experienced. This is the future that physics actually allows. Not a galaxy filled with our descendants spreading from star to star and waving at each other across the void. A handful of isolated remnants, slowly running out of resources, eventually going dark, in a universe that has stretched apart so completely that no two civilizations could ever again find each other. And there is one more wall, one more limit that needs to be considered. The wall of available energy. Every act of civilization requires energy. Every act of expansion requires more energy. Light cannot be the medium of meaningful interstellar communication because it takes too long to cross the distances involved. But matter, real matter, the substance of any colony ship or probe or settlement, requires enormous energy to accelerate and decelerate. To send even a small probe to Proxima Centauri at a meaningful fraction of light speed requires energy comparable to the total annual energy production of the entire human civilization on Earth. To send a larger ship, a colony ship, takes correspondingly more. To send a wave of such ships outward to dozens or hundreds of nearby stars takes more still. And the deeper into the cosmos you go, the more energy each new outpost demands. The Russian astronomer Nikolai Kardashev formalized this in 1964 with a classification scheme that is still used today. A Type 1 civilization harnesses all the energy available on its home planet. A Type 2 civilization harnesses all the energy of its home star. A Type 3 civilization harnesses the energy of its entire galaxy. Humanity is currently at approximately 0.7 on this scale. We have not yet reached Type 1. We do not yet control even the energy budget of our own planet. The leap to Type 2 would require us to build structures around our Sun that capture a significant fraction of its total energy output. Dyson swarms, or partial Dyson spheres, vast arrays of orbiting collectors that surround a star and harvest its light. The materials needed to construct such a structure would require disassembling most of the inner solar system, possibly including Mercury. The engineering challenges are immense. The energy budget required to begin construction is itself many times larger than humanity has ever produced, but the laws of physics permit it. It is, in principle, achievable. The leap to Type 3 is harder by an enormous margin. Harvesting the energy of an entire galaxy requires constructing Dyson swarms around hundreds of billions of stars. It requires coordinating that construction across distances so vast that light takes 100,000 years to cross them. It requires sustaining the project for millions of years. It is the kind of undertaking that would dwarf anything humanity has ever attempted by factors that have no intuitive meaning. And once you have done it, you are at the maximum size that the universe permits. There is no Type 4 civilization in Kardashev's scheme, no civilization that harnesses the energy of an entire galaxy cluster or supercluster. Some thinkers have proposed it, but the math does not work. Because of the cosmological event horizon, no civilization can ever have access to the energy of a structure larger than its own gravitationally bound region. The energy of the galaxies beyond the local group is forever beyond reach. The dark energy that powers the expansion of space ensures that any attempt to gather energy from those distant galaxies would fail. You cannot harvest what you cannot reach. You cannot collect from sources that are moving away from you faster than you can chase them. So the maximum energy budget available to any civilization originating on Earth is approximately the total energy output of every star in the local group, sustained for the duration of the stelliferous era. That is a finite number. It is a very large finite number. But it is a finite number. And once it is exhausted, the civilization has no further source of energy except the cooling remnants of dead stars and the slow trickle of Hawking radiation from black holes. There is a final stage of cosmic engineering that some physicists have speculated about: the harvesting of energy from evaporating black holes. Black holes, according to the calculations of Stephen Hawking, slowly leak particles and radiation from their event horizons over enormously long timescales. A stellar mass black hole evaporates completely in approximately 10 to the 67 power years. A supermassive black hole takes 10 to the 100 power years. These timescales are so vast that they make the entire current age of the universe look like an instant. But within those timescales, a civilization that has learned to extract useful energy from Hawking radiation could in principle continue to exist long after all the stars have died. It would be a strange kind of existence. The energy yields are tiny, the available raw materials are sparse. The civilization would be more like a slow-motion conservation effort than a flourishing society. But it could continue for trillions, quadrillions, perhaps even longer durations if the engineering challenges could be solved. And this is, in the end, the realistic upper bound on humanity's cosmic future. Not a galactic empire spanning trillions of stars, not a civilization that fills the universe. A small, isolated, eventually post-stellar community descended from a wave of colonization that reached as much of the local group as physics permitted, slowly running down the energy budget of its enclosed cosmic neighborhood, until even that runs out. The walls are too many and too high. The cosmological event horizon, the speed of light, the expansion of space, the finite supply of stars and energy within the gravitationally bound region, the biological and engineering challenges of surviving across millions of years. Together, they constrain any expansion to a sphere far smaller than the dreams of science fiction have ever imagined. And here is the thought that should perhaps be most disturbing of all. Even if humanity manages to spread to the maximum extent that the universe permits, even if we colonize every habitable world in the local group, even if we build Dyson swarms around every star, even if we extract every last drop of energy from every collapsing system, we will still occupy less than 0.00001% of what is currently visible in our sky. The remaining 99.99999% of the cosmos, the trillions of galaxies beyond our reach, will go about their existence completely independent of anything we do. Stars will be born and die there. Planets will form and host life. Civilizations may arise, cultures may flourish, histories may unfold across billions of years. And none of it will ever be touched by us, or by anything we have built, or by anything we have ever known. The universe is too big. Not too big for us to map, not too big for us to study, but too big for us to inhabit, too big for us to spread across, too big for us to fill, or shape, or claim. We can see it. We cannot have it. Most of it was never going to be ours. There is a particular grief in this realization that I think is worth sitting with for a moment, because it changes how we should think about the question of what humanity is doing here. For most of recorded history, humans have lived inside stories that promised expansion, growth, continuation. Religions promised eternity. Empires promised dominion. Scientific civilization promised conquest of the natural world. The implicit assumption behind all of these stories was that the universe was a kind of open frontier, available in principle to any civilization with the will to take it. The discovery that the universe is not open, that it has walls, that those walls are closing, runs against everything our species has assumed about its future, and it raises a question that we do not really have the cultural vocabulary to answer. If we cannot fill the cosmos, what are we for? If our maximum reach is a tiny isolated bubble in an enormous dispersing emptiness, what does it mean to be a civilization at all? One answer, the answer that most modern cosmologists and futurists give when pressed, is that the limits do not really matter. That what matters is what we do with the time and space we have, not the totality of the universe. That a civilization can have meaning, can flourish, can produce beauty and knowledge and depth of experience within its allotted region, without needing to spread across all of creation. That the proper measure of a civilization is not how much it occupies, but how richly it lives. This is a satisfying answer in some ways. It is the answer of philosophers and contemplatives across thousands of years. The universe is what it is. We are what we are. The proper response is not to grasp for what is impossible, but to live well within what is possible. But the answer also requires us to give up something that humanity has clung to for a very long time. The dream of unlimited growth. The vision of a species that goes on expanding forever, becoming greater, becoming more, becoming a presence in the cosmos that cannot be ignored. That dream, when measured against the actual physics of the universe, turns out to be a fantasy. And the question of how we live without it is one that our cultures have not yet figured out how to answer. There is one more possibility that we should consider before we close this part of the story. It is the most speculative possibility of all, and it depends on physics that we do not yet fully understand. But it is the only possibility that would let humanity escape the walls we have been describing. The possibility of breaking the rules. If general relativity is, as some theoretical physicists suspect, an approximation to a deeper theory of gravity, then there may be ways to manipulate space-time that the current rules do not permit. Wormholes, traversable shortcuts through the fabric of space, could in principle allow travel between two distant regions in less time than light would take to traverse the same path through normal space. The Alcubierre warp drive, proposed in 1994, describes a way to compress space in front of a spacecraft and expand it behind, effectively allowing the craft to move faster than light without violating relativity locally. Both ideas require exotic matter with negative energy density, a substance that may or may not exist anywhere in the universe in sufficient quantities to be useful. Quantum effects suggest that small amounts of negative energy are possible, but extracting and concentrating it on the scales needed for interstellar travel may be impossible in principle. The current consensus among physicists is that warp drives and stable traversable wormholes are probably forbidden by the actual laws of nature, even if they are not strictly forbidden by the equations of general relativity. But probably is not the same as definitely. And the history of physics is full of moments when something that seemed impossible turned out, on closer examination, to be only difficult. If a future civilization, perhaps thousands of years from now, discovered a way to manipulate space-time that bypassed the speed of light barrier, the walls we have been describing would be torn down. The cosmological event horizon would no longer be a hard limit. Galaxies beyond it could be reached. The universe could become open again. This is the hope that science fiction has always held on to. The faint possibility that the rules we currently know are not the final rules. That somewhere in the deeper physics we have not yet discovered, there is a loophole large enough for a civilization to slip through. It is a thin hope. The physical evidence against it is substantial. The exotic matter required does not appear to exist. The energy requirements, even in the most optimistic models, are astronomical. And no laboratory experiment has ever produced any indication that faster-than-light travel is achievable. But hope, particularly hope tied to the deepest questions about what a species can be, is not easily extinguished. So we should at least acknowledge the possibility. The possibility that the walls we are describing tonight are the walls of the current universe as we understand it, not the walls of all possible universes that humanity might someday learn to inhabit. The possibility that we are still, after centuries of progress, only at the beginning of our understanding of what reality permits. Maybe the cosmic event horizon is not the final word. Maybe there are still discoveries waiting, still principles of nature we have not yet grasped, still doors that might one day open. Maybe. But for now, for the universe as we currently understand it, the walls are real, they are closing. And they define the maximum size of any civilization that could possibly emerge from this planet or from any other planet within our reach. So when we ask the question that gave this exploration its title, how far could humanity spread before the universe stops us, we have to give an answer that is at once specific and humbling. We can spread, with maximum effort and maximum luck, to perhaps 1 out of every 20 million stars that we currently see. We can occupy a sphere encompassing our local group, possibly extending slightly into the Virgo supercluster if we move quickly. We can fill that sphere with colonies, with probes, with engineered structures, with whatever forms of civilization we are capable of building. And then we stop. Not because we run out of will, but because we run out of universe. Because the rest of the cosmos has carried itself beyond our reach. Because the dark energy that fills empty space is stronger than anything we know how to build. Because the geometry of an expanding universe is built to keep its inhabitants apart. The wall closes. The horizon contracts. The remaining galaxies fade beyond detection. And we are left, finally, with what we always had. Our local group. Our merged Milkomeda galaxy. A handful of nearby companions. A finite collection of stars whose number, however large, is forever bounded. This is the inheritance that physics gives us. Not the universe. A particular piece of it. A particular brief window in cosmic time. a particular gravitationally bound island in an ocean that is rapidly emptying. And the question of what we do with that inheritance, of how we use the centuries and millennia and possibly millions of years that the laws of nature allow us, is the only question that ultimately matters. There is one more piece of this story that we have not yet examined, and it is perhaps the most haunting of all. Because the walls do not only close from the outside, they also close from the inside. There are limits on how long any civilization can survive, even in principle, even with perfect technology and perfect cooperation and perfect resource management. And those limits, when you actually do the calculations, are far shorter than the upper bound on the Stelliferous Era. The Stelliferous Era will continue for 100 trillion years. But complex life as we currently understand it is unlikely to survive anywhere near that long. The reasons are many, and they compound on each other. The home star changes over time. Our own sun, currently in the middle of its main sequence lifetime, will gradually grow hotter and brighter over the next billion years. In approximately 600 million to a billion years from now, the increasing solar luminosity will likely raise Earth's surface temperature past the point where liquid water can exist. The oceans will begin to evaporate, the greenhouse effect will run away. Earth, long before the sun finally swells into a red giant and engulfs the inner planets in 5 billion years, will become uninhabitable for surface life. This means that humanity, if we wish to survive on cosmic timescales, must leave Earth long before our current home becomes lethal. We have approximately 500 million years to develop the technology and infrastructure to relocate. That is a tight schedule by cosmic standards. It is a generous schedule by human historical standards, which span only about 10,000 years of civilization. But it is finite. Other star systems face their own deadlines. Stars more massive than the Sun burn faster and die younger. Stars less massive than the Sun live longer, but emit less light, and may be too dim to support complex biosphere over geological time. Red dwarfs, the longest-lived stars, are also the most prone to violent flaring, and any planets in their habitable zones face constant bombardment by stellar radiation that may sterilize their surfaces. Even in the most optimistic case, every star system has a finite window in which it can host a thriving civilization. And once that window closes, the civilization must move on, or end. Moving on takes time. It takes energy. It takes the ability to coordinate across enormous distances and to maintain cultural continuity across generations of crew who will never see their starting point or their destination. Every relocation is a risk. Every transition is an opportunity for the chain to break. And the chain has to remain unbroken for the entire duration of any civilization that hopes to survive across deep time. And the longer you try to extend the chain, the more failure modes you encounter. There are catastrophes that no civilization can engineer its way around. Nearby supernovae, gamma-ray bursts, asteroid impacts. The eventual collision of the Milky Way and Andromeda will throw entire star systems into chaos. The merger of the local group into a single elliptical galaxy over tens of billions of years will disrupt orbits, eject planets, swallow stars into the central black hole. Any civilization that manages to survive into that era will have lived through the dissolution of the celestial geography that gave rise to them. They will have watched their home galaxy be destroyed and rebuilt. They will inhabit a transformed universe that bears little resemblance to the one we currently see. And the further you go beyond that, the stranger and more hostile the cosmos becomes. After the Stelliferous Era ends, the universe enters what physicists call the degenerate era. The bright stars are gone. The galaxies are dim and depleted. The dominant objects in the universe are white dwarfs, the cooling cores of dead stars, slowly fading from white to red to brown to black over trillions of years. Some neutron stars persist, ancient compressed remnants of stellar collapse. But they too are cooling. Black holes are everywhere, the gravitational anchors of every former galaxy, slowly accumulating the dead stellar matter that drifts into their pull. A civilization surviving into the degenerate era would inhabit a universe where the dominant source of energy is the slow trickle of accretion onto compact remnants, supplemented perhaps by the careful engineering of brown dwarf collisions. a process that physicists have speculated could create new stellar fusion reactors out of the cooling remnants of failed stars. It is not a lively universe. It is a universe of slow, careful conservation, of meager energy budgets, of long stretches of darkness punctuated by occasional brief flickers of activity. But it could continue. With sufficient ingenuity, a post-stellar civilization could survive for hundreds of trillions of years, possibly longer. They would be cold, quiet, sparse, but they would be alive. They would inherit a strange, dim, depleted version of the cosmos. And they would still be confined to the gravitationally bound remnants of the local group, because everything else would have long since vanished beyond the cosmological event horizon. Eventually, even the degenerate era ends. We are now talking about timescales that have no human meaning. 10 to the 30 power years, 10 to the 40 power years. Numbers that exceed the current age of the universe by amounts so vast that comparison is essentially impossible. At some point in this distant future, if the predictions of certain grand unified theories of particle physics are correct, even the protons that make up ordinary matter will begin to decay. They will dissolve into lighter particles. Atomic nuclei will dissolve. White dwarfs and neutron stars and brown dwarfs will gradually evaporate, their atoms unraveling into radiation. The universe will become a thinning haze of photons and electrons and other elementary particles, spread across an unimaginably expanded volume of space. By the time this is finished, perhaps after 10 to the 40 power years, very little will remain of what was once matter. The universe will be approaching, though never quite reaching, the maximum entropy state. The configuration in which nothing interesting can happen, in which no work can be done, in which no order can be sustained. Heat death. The final calm. Within this enormous span, black holes are the longest-lasting structures. They persist because their gravity is so intense that they outlive even the decay of ordinary matter. But black holes are not eternal either. They evaporate through Hawking radiation, emitting particles slowly over timescales that depend on their mass. A solar mass black hole takes about 10 to the 67 power years to fully evaporate. A supermassive black hole, the kind that sits at the center of a galaxy, takes 10 to the 100 power years. These numbers are so vast that they make the entire history of the universe up to this point look like the first nanosecond of a much longer story. But they are still finite. Even black holes end. And once they end, the universe contains essentially nothing. A diffuse cooling bath of photons and a few residual particles spread across a volume that has expanded beyond comprehension. The end. The actual end of the cosmic story, as far as our current physics permits us to predict it. And humanity, if humanity is somehow still around in any meaningful sense, has been confined throughout this entire history to the increasingly small, increasingly cold, increasingly dim remnants of our local group. We cannot outlast the universe. We can perhaps outlast the stars. We can perhaps survive into the era of black hole evaporation. But we cannot continue forever. The walls close around us and around any civilization until eventually they close completely. So how far could humanity spread before the universe stops us? The honest answer, the answer that emerges when you put all the physics together, is this. We could spread, if everything goes maximally well, to perhaps every star within 100 million light-years of Earth, roughly. With ambitious engineering and a great deal of luck. That is the bound. That is the most that physics permits any civilization originating on this planet to occupy. It includes the Milky Way, the Andromeda Galaxy, the rest of the local group, and possibly some of the nearer galaxies in the Virgo supercluster if we move quickly. It contains, very roughly, 10 quadrillion stars. It excludes, definitively, the other 2 trillion galaxies in the observable universe. We can see them, we cannot have them. They are part of the same cosmos that produced us, but they will never be part of any story we tell. And the time available to us, the duration over which a civilization could in principle thrive within that bounded sphere, is also finite. The stelliferous era provides perhaps 100 trillion years of energy from stars. The degenerate era provides additional billions of years of slow conservation and engineering. The black hole era provides whatever final epoch is possible while extracting energy from evaporating singularities. After that, nothing. Some philosophers have called this picture nihilistic. They say it strips meaning from everything. If we cannot fill the universe, if everything we build will eventually fade, if no civilization can be eternal and no expansion can be unlimited, then why bother? Why try to spread at all? Why try to do anything? I think this is the wrong way to read what the universe is telling us. The cosmos does not owe us infinity. It never did. The fact that we, briefly, get to exist at all in a universe whose laws and structures could just as easily have produced no observers, no consciousness, no comprehension, is the actual miracle. The fact that our particular evolutionary lineage produced a species capable of looking up at the night sky and calculating the size of what we cannot reach is itself remarkable. The walls are real. They are also late. They close, eventually, but not yet. And while they have not finished closing, we have time, we have stars, we have potential destinations, we have entire worlds that no human has ever touched, waiting in the dark within our local group, within our nearby galactic neighborhood, within our gravitational island in the slowly dispersing sea. There is a calculation that the physicist Freeman Dyson once did that I find particularly haunting on this point. Dyson asked whether a civilization that managed its energy carefully could continue thinking, processing information, having conscious experiences across the deep cosmic future even as the universe ran down toward heat death. He concluded that under certain assumptions the answer was yes. By slowing its metabolism, by carefully matching its computational rate to the available energy budget, by extracting work from the slow temperature differences that would persist even in a cooling universe, a civilization could continue to have meaningful experiences for an unbounded amount of subjective time. Not infinite time, but effectively unbounded. The number of total experiences possible would be limited by energy, not by time. As long as the civilization adapted, slowed, conserved, the experiences could continue. This was a hopeful picture, in its way. A civilization that had given up on expansion, that had accepted the walls of the cosmos, but that had decided to continue thinking and feeling and creating for as long as physics permitted. Later work in cosmology cast doubt on parts of Dyson's calculation. The discovery of accelerating expansion, in particular, makes some of his original scenarios unworkable. The universe will become cold faster than he anticipated. The energy available for sustaining thought will dwindle more quickly. But the basic insight remains. A civilization does not need to expand in order to matter. It does not need to occupy more space in order to be valuable. The value lies in what it does, what it creates, what it experiences, what it understands, within whatever space and time it has been granted. And on that measure, humanity has barely begun. We have existed as a species for about 300,000 years. We have had civilization for about 10,000. We have had science as a systematic enterprise for about 400. We are not at the end of the story, we are at the very beginning of it. The walls that will eventually close around us are not going to close for another 100 billion years at the earliest, and most of them will not close meaningfully for trillions of years more. We have so much time, we have so much potential reach. We have so much that remains to be done, to be seen, to be understood, before any of the cosmic walls we have been discussing tonight become actually limiting rather than merely theoretically limiting. But the discovery that the walls exist at all changes how we should think about that time. It changes the meaning of the choices we make now. If humanity were truly an unlimited species, with infinite time and infinite space, then any particular decade or century or millennium would matter very little. There would always be more, always be later, always be elsewhere. The discovery that the walls are real, that the reachable universe is shrinking, that every delay in expansion permanently subtracts from the maximum size we could ever achieve, gives this moment in human history a weight that previous generations did not understand. We are not living in an open frontier. We are living inside a closing room. The room is enormous, and the closing is slow, but it is happening. And the question of what we do with the room while we still have access to it is the only question that ultimately matters. There is a sense in which humanity right now is alone, in a way that no previous generation has truly understood. We are the first generation that knows how the walls are constructed. We are the first generation that can calculate with some precision how much of the cosmos is reachable and how much is already lost. We are the first generation that can look at the night sky and understand that most of what we see is, in a meaningful sense, no longer ours. This knowledge places a kind of cosmic responsibility on us, not because we have to do anything in particular, but because we have to know what we are doing. We cannot pretend that the universe is unlimited. We cannot pretend that the future will always be open. We have to make our choices about expansion, about resource use, about long-term survival, with the full awareness that the cosmos is, in its slow, patient way, closing around us. And the choices we make in the next few thousand years will determine, perhaps in irreversible ways, how much of what is still possible we actually achieve. There is one more thread I want to pull on before we begin to bring this exploration to its close. It is the question of what other civilizations, if they exist, are doing about the same problem. Because if the walls are real for us, they are real for them too. Every intelligent species in the universe faces the same constraints: the speed of light, the cosmological event horizon, the finite resources of a gravitationally bound region, the limits of what physics permits. Every alien civilization that has ever existed has been confined to the same kind of cosmic island that humanity inhabits, just centered on a different point in space. And here is the unsettling implication. The walls separate civilizations from each other just as effectively as they separate civilizations from unreachable galaxies. The civilizations within our own local group, if any exist, could in principle be reached. We could send probes. We could make contact. We could potentially learn from them, trade with them, become part of a larger interstellar community within the bounded region we share. The civilizations beyond the local group, even if they exist in great numbers, are forever beyond reach. We could never visit them. We could never communicate meaningfully with them. Even a signal sent at the speed of light would, in many cases, never arrive, because the space between us is expanding faster than the signal can cross it. So the cosmological event horizon is not just a wall around humanity. It is a wall around every civilization that has ever existed. It divides the universe into causal islands, each one cut off from all the others, each one limited to its own gravitationally bound region. The cosmos may be full of civilizations. We will never meet most of them. We cannot meet most of them. The geometry of an expanding universe forbids it. And this means that even if life is common, even if intelligence is common, even if technological civilization is common, the cosmos is structured to keep them all apart. Every civilization sees a sky full of galaxies. Every civilization can see the lights of countless other potential homes. Every civilization knows that those lights are unreachable. We are each, in our own way, alone in the same way, surrounded by an immense visible cosmos that we can study but cannot touch, connected to a small, bounded region that we can in principle inhabit, cut off permanently from the rest. This is not science fiction. This is the actual structure of the universe as physics has revealed it. The Fermi paradox, the silence of the cosmos, the absence of evidence for any other civilization, may have many explanations, but one of them, perhaps the saddest, is simply that even if they are out there, the universe was built to keep us from finding them. The walls were closing for them too. They had their own local groups, they had their own bounded regions. And whatever they built, however they spread, however far they extended themselves before whatever filter ended their story, they remained in their own cosmic neighborhood, separated from us by an expanding emptiness that no civilization can cross. Imagine, just for a moment, that there is a civilization right now in the Andromeda galaxy that has been thriving for 10 million years. Imagine that they have spread across their galaxy. Imagine that they have built Dyson swarms around tens of billions of stars. Imagine that they look out at the night sky from their home worlds and wonder, as we do, whether they are alone. From their perspective, the Milky Way is one of the galaxies they could in principle reach. We are within their cosmic island, just as they are within ours. If they sent probes our way, those probes could eventually arrive. If we sent probes their way, ours could eventually arrive. But the journey is 2.5 million years. The timescales are too long for any conventional civilization to sustain. Even if they exist, even if they are trying, The gap between us is so vast that meaningful contact is almost impossibly difficult. And outside the local group, the situation is worse by orders of magnitude. There may be 1,000 civilizations within the Virgo supercluster, each one in its own galaxy, each one separated from all the others by millions of light-years of intergalactic space, each one increasingly isolated as the universe expands. They might as well be in separate universes. The geometry forbids them from forming any meaningful community. Each one is its own story, its own beginning and middle and end, played out in its own corner of the bounded sphere that the universe permits. And beyond the Virgo supercluster, in the trillions of galaxies that lie outside our reachable region entirely, there may be countless civilizations whose existence we will never confirm, whose stories we will never know, whose triumphs and tragedies will play out completely independently of anything we ever do. The universe is full of stories. We get to live exactly one of them, in exactly one corner of it. The rest is forever closed. This is the cosmic context in which humanity finds itself, small, brief, bounded, alone, looking out at an immense visible universe that is, in its actual structure, a collection of separate islands rather than a unified ocean. The cosmos is not one thing, it is many things, each one isolated from the others by walls that no engineering can ever overcome. We are on one of those islands. We are early in our island's history. We have, by cosmic standards, a great deal of time still ahead of us. But we will never know what is happening on the other islands. We will never visit them. We will never receive a signal from them. Whatever they are doing it for themselves in their own bounded region, with no hope of contact with anyone outside their cosmic neighborhood. And the realization that this is true changes something important about how we should think about our own civilization. It changes what we should value. It changes what we should preserve. If we are alone in the sense that no help is coming from anywhere else, that no other civilization can save us or replace us, that whatever we lose is lost permanently, then everything we have becomes precious in a way that an unlimited universe would not allow. Every species we drive to extinction is gone forever. Every culture we let die is gone forever. Every body of knowledge we fail to preserve is gone forever. There is no backup. There is no parallel civilization elsewhere in the cosmos that will independently rediscover what we let slip. The cosmos does not provide redundancy. Each island is its own complete and final story. So when we ask what we should do with the time and space the universe has granted us, the answer cannot be simply expansion. The answer cannot be growth for its own sake, conquest for its own sake, occupation for its own sake. The walls ensure that any project of expansion has a final upper bound. The real question is what we make of the inheritance, what we build, what we preserve, what we discover, what we pass on to whatever forms of intelligence and consciousness might continue after us within the bounded region we share. And here, I think, is the closing thought that the physics of this question keeps bringing us back to. The cosmos was not designed for any purpose. It is not built to favor or disfavor any species. The walls that close around us are not punishments. They are simply consequences of how the laws of nature happen to work. Dark energy did not choose to push space apart. It is doing what its nature dictates. The cosmological event horizon did not choose to limit any civilization. It emerged from the geometry of an expanding space-time. The speed of light did not choose to be the absolute upper bound on travel and communication. It is built into the structure of space-time itself. These limits are impersonal. They are not aimed at us. They would close around any species, any civilization, any conscious form of life, anywhere in the universe. So in a sense, the walls are not stopping humanity from reaching the universe. The walls are defining what the universe means for any inhabitant of it. They are part of the cosmic environment that every species shares, the inheritance that every civilization must come to terms with. The proper response to discovering them is not despair. It is recognition. It is the kind of mature acceptance that allows a species to plan realistically for the future, to allocate its energy and attention appropriately, to value what it has, and to use its time well. There is so much that humanity could still do. There are so many stars still potentially reachable. There are so many worlds in our galaxy alone that no probe has ever visited. There are so many questions about physics, about chemistry, about biology, about consciousness that we have not yet begun to answer. There is so much beauty still to be created, so much knowledge still to be discovered, so much depth of experience still to be lived. The walls give us a finite stage, but they leave us, for now, with an enormous one. We are not at the end. We are at the beginning of what can be done within the bounded region that the universe has granted us. The fact that the region is bounded does not diminish what can happen inside it. It only means that whatever we do for the inhabitants of this island and for whatever comes after them within the same bounded inheritance. The night sky tonight, the sky you might walk outside to see after this video ends, contains thousands of stars visible to your unaided eye. All of them are within our galaxy. All of them are within our reach, in principle, given enough time and effort. Beyond them, with a telescope, you could see the Andromeda Galaxy, a faint smudge of light that is the most distant object visible to the unaided eye under perfect conditions. 2.5 million light-years away, the most distant thing you can see without instruments. And it is, in principle, reachable. It will be part of our merged galaxy in a few billion years. It is one of the cosmic neighborhoods that humanity could potentially inhabit. Beyond Andromeda, with progressively more powerful telescopes, you could see the galaxies of the local group, then the galaxies of the Virgo supercluster, then the galaxies of the Coma cluster, the Hercules cluster, the great wall of structure that maps the cosmic web at our scale. All of those, beyond the local group, are already in motion away from us, already receding, already in many cases beyond reach. The light from them in our telescopes is the light of ghosts. We are looking at ancient images of places we will never go. And beyond those, with the most powerful instruments humanity has ever built, the James Webb Space Telescope and the deep field surveys and the maps of the cosmic microwave background, we can see galaxies that existed within the first few 100 million years after the Big Bang. We can see the very oldest structures that ever formed. We can see almost to the beginning. And almost all of what we can see is beyond reach. The observable universe is enormous. The reachable universe is small. The gap between what we can see and what we can have is one of the most profound facts about the cosmos we inhabit. So when you look up at the night sky tonight, when you see the familiar constellations and the dim band of the Milky Way and the faint smudge of Andromeda on the horizon, remember what you are actually looking at. You are looking at the boundary of your cosmic inheritance. You are looking at the maximum reach of any civilization that humanity could ever build. The stars you can see, plus a few 100,000 more in the local group, plus perhaps a small number of nearby galaxies, are the totality of what is on offer. Everything beyond it has already been carried away by the expansion of space. And yet, despite this, despite the walls and the closing horizons and the impossibility of ever reaching most of what we can see, there is something extraordinary about our situation that I want to leave you with as we move toward the close of this exploration. It is the fact that we can see at all. It is the fact that consciousness, briefly, in this corner of one galaxy on one filament of the cosmic web, has emerged and looked outward and asked these questions and worked out the answers. The universe, for most of its history, contained no observers. The first few 100 million years were too hot for any form of complex matter. The next billion years contained only simple stars and unevolved galaxies. The first life on any planet anywhere in the cosmos probably did not arise for several billion years after the Big Bang. Intelligence took longer still. On our own world, conscious thought has existed for, at most, a few 100,000 years. The capacity to do cosmology, to understand the structure of the universe, to calculate the limits of our own future, has existed for, perhaps, a century. We are an extraordinarily new arrival in a very old universe, and we are also extraordinarily early. There may be civilizations that arise hundreds of billions of years from now, on planets orbiting red dwarf stars that have not yet finished forming. There may be civilizations that arise late in the Stelliferous era, in conditions vastly different from ours. We are not at the middle of the cosmic story. We are very close to the beginning. We have one of the longest possible runways of any civilization that could ever exist. We have, if we manage ourselves carefully, a future that could span billions of years. That is something to take seriously. That is something worth protecting. The walls are real. They will close eventually. But not yet. Not for a very long time yet. And in the time that remains, we have the opportunity to do things that no civilization that arises later in cosmic history will be able to do. We can witness the universe in its current, rich, structured, observable state. We can see other galaxies. We can observe the cosmic microwave background. We can study the deep history of the cosmos. We can build the science and the philosophy and the culture that will be passed on, in whatever form, to whatever inhabitants of our bounded region come after us. We are the cosmos becoming aware of itself, briefly, in this particular place, at this particular time. The walls do not erase that. They only define the stage on which it is happening. There is one final consideration that physics has been pressing toward in recent decades, and it is perhaps the most disorienting of all. It is the possibility that the cosmological event horizon is not the only horizon that matters. That our universe itself may be one of many. That beyond the boundaries of what we can observe, beyond the walls of our own bounded sphere, there may be other regions of space-time entirely, with their own physics, their own histories, their own consciousnesses. The theoretical framework that suggests this is called the multiverse, and it comes in several forms. The inflationary multiverse proposes that the rapid expansion of the very early universe, the process that produced what we now call the observable universe, never actually stopped everywhere. It is still happening in regions of space far beyond our horizon, producing other bubble universes that are completely isolated from ours. The quantum many-worlds interpretation proposes that every quantum event splits reality into multiple parallel branches, each one carrying forward as its own complete cosmos. The string theory landscape proposes that the laws of physics themselves can take many different forms in different regions, with our universe being just one of an enormous number of possible configurations. None of these theories is currently provable. None of them yields predictions that we can directly test with current technology. They remain speculative, mathematical, suggestive, but they raise the possibility that the walls we have been describing tonight are walls only around our particular universe, not around all of existence. The cosmos as a whole, the multiverse, may be vastly larger and more varied than anything our telescopes will ever see. We are confined to one bubble. There may be infinitely many other bubbles. We will never reach them, never observe them, never know what they contain, but they may be there. And in some strange way, that possibility offers a kind of comfort. Not because we will ever participate in those other realities, but because it suggests that the cosmos, the deepest level of reality, is so unimaginably vast that even our limitations cease to be the final word. The universe we can see is a small piece. The universe we can reach is smaller still. But the totality of existence may be larger than any of our walls. Beyond them, perhaps, the story continues in ways we cannot follow, but can dimly suspect. And in that suspicion, in the possibility that the cosmos is even greater than we have measured, there is something that the walls themselves cannot take away. The wonder, the awareness that we exist at all, the capacity to ask the question of how far we could spread, and to answer it, and in answering it, to glimpse just how much more there is to existence than even the most ambitious civilization could ever hope to touch. Let us come back, finally, to the question that started this exploration. How far could humanity spread before the universe stops us? After everything we have considered, the cosmological event horizon, the speed of light, the expansion of space, the finite resources of any gravitationally bound region, the deep limits of energy and entropy and time, we can give an answer that is both specific and humbling. Humanity, with maximum effort and maximum luck, could spread to occupy approximately the volume of our local group of galaxies, and possibly a portion of the Virgo supercluster. That is the upper bound. That is the farthest we can ever go. The remainder of the universe, the trillions of galaxies that currently fill our deep field telescope images, the ancient structures stretching back to the first 100 million years after the Big Bang, all of them are already lost, not difficult to reach, lost, permanently outside the boundary of what physics permits. Our maximum reach is roughly one star out of every 20 million we can see. The other 99.999995% of the cosmos belongs to no civilization originating on Earth. It will go on its way, expanding, dispersing, evolving, dying, completely independent of anything humanity ever does. We will see it as ancient light for as long as our descendants have telescopes capable of detecting it. We will study it as best we can, and we will know with the certainty that only physics can provide that we will never touch it. And within the bounded region we can reach, our occupation will not be the unified empire of science fiction. It will be a constellation of isolated outposts, each one separated from the others by gulfs of time and distance that no civilization can fully bridge. Communication between any two distant colonies will be measured in centuries or millennia. Cultural drift across that span is inevitable. Each settlement will, over generations, become its own civilization, related to ours by ancestry but distinct in every other way. The humanity that arrives in Andromeda will not be the humanity that left Earth. The humanity that survives into the degenerate era will not be the humanity that exists today. We will become many things, and most of those things will lose contact with each other, and eventually all of them will fade. This is the maximum future. This is what physics permits at the upper bound. And the timeline matters as much as the size. To reach even this maximum, humanity would need to begin a serious effort within the next few 100 million years, before our own star starts to make Earth uninhabitable, before the local conditions for civilization begin to deteriorate. We have a window. The window is wide by human standards but narrow by cosmic ones. Every century we wait, every millennium we spend without serious investment in interstellar capability, the practical reach shrinks. The galaxies at the edge of our potential sphere drift further. The energy required to chase them increases. The probability of catastrophe before we can establish a self-sustaining presence beyond Earth grows. Time is not on our side, not in the long run. It is on no civilization's side. The universe is patient with no one. So when we ask what we should do with the time we have, the answer that emerges from cosmology is not despair. It is urgency, not the urgency of crisis, but the urgency of opportunity. We are in possession, briefly, of a state of the cosmos that will not exist forever. We can see structures that future civilizations will not be able to see. We can reach destinations that future civilizations will find already lost. We can do science that will become impossible once the cosmological event horizon contracts enough to put the cosmic microwave background out of detection. We are, in a real and measurable sense, the lucky generation. We exist at the moment when the universe is still observable and still partially reachable. Future inhabitants of our bounded region will look out at a much emptier sky. They will have fewer galaxies to study, fewer destinations to consider, fewer cosmic phenomena to investigate. They will inherit a smaller, dimmer, lonelier cosmos. The knowledge we accumulate now, the understanding we develop now, the structures we build now, will be the inheritance we pass to them. They will not be able to redo our work. They will not be able to discover what we failed to discover. The window is now. The opportunity is now. Whatever humanity is going to accomplish in this universe, the foundations for it are being laid in this era, by us, in this brief stretch of cosmic time when the lights are still on and the doors are still partly open. There is a particular image I want to leave you with. Imagine, 10 billion years from now, a civilization that has descended from us, living in some surviving star system within the merged remnant of the local group. The Milky Way and Andromeda have long since collided. The dwarf galaxies have been absorbed. The local group has compacted into a single enormous elliptical galaxy. Outside that galaxy, in every direction the sky is empty. Every other galaxy that once existed in the observable universe has long since crossed the cosmological event horizon and disappeared. The cosmic microwave background has redshifted to wavelengths so long it can no longer be detected with any practical instrument. The history of the universe before the merger is no longer visible. From the perspective of that future civilization, there is only one galaxy, their own. Surrounded by black emptiness, extending in every direction, they might not know that anything else ever existed. If their cosmology has been preserved from older eras, they will have records. They will have inherited knowledge from us, telling them that once the sky was full of other galaxies, that there were once 2 trillion of them visible from our location, that the universe was, in some distant past, observably enormous. They will read these records as a kind of legend. A story about an ancient era when their cosmic neighborhood was part of something vastly larger. But they will not be able to confirm any of it. The evidence will be gone. The other galaxies will be unreachable, unobservable, unverifiable. The science of cosmology, as we currently practice it, will be impossible for them. They will know only their own galaxy. They will study only their own stars. Their universe, observationally, will be much smaller than ours. And the knowledge that the universe was once larger, that other galaxies once existed, that the cosmic microwave background once filled the sky with the afterglow of creation, will be a gift from us, a piece of inheritance that we pass forward across time. Without our records, they would not know. With our records, they will know but cannot confirm. They will live in a universe that has, in a profound sense, hidden most of itself from them. And we, briefly, will have been the witnesses to the version of the cosmos that included everything. This is a strange and beautiful responsibility. We are the generation, or at least the era, that gets to see the cosmos in its richest observable state. Not the oldest cosmos. That was hidden behind the wall of the cosmic microwave background, opaque to all forms of light. Not the final cosmos. That will be largely empty and dark. The middle period, the moment when structures exist in great variety, when galaxies are everywhere, when light can still travel across vast distances and carry information from billions of years ago. This is the era of maximum visibility. And it is also the era in which the walls have begun to close but have not yet closed completely. The reachable region is shrinking, but it is still vast. The unreachable region has already swelled to encompass most of what we see, but the part we can still touch is still enormous by any human standard. We are in the brief window between the early universe and the late universe, when there is still enough left to reach, still enough left to study, still enough left to inhabit, and the choices we make in this window will determine, in part, what humanity becomes. Whether we ever leave Earth in serious numbers, whether we ever build the engineering required to reach other stars, whether we ever establish a presence in another galaxy, whether we ever, in our maximum form, occupy a meaningful fraction of the volume that the universe permits. These are not just technical questions. They are existential questions about what kind of species we want to be. And the timeline for answering them, while long by human standards, is not infinite. I want to end with one more thought, because I think it captures what is most important about all of this. The universe is not built for humanity. It is not built against humanity. It is simply built. It follows its own laws, expressed in equations that have nothing to do with our preferences or our hopes. Dark energy expands space at a rate that pushes most of the cosmos beyond our reach. The cosmological event horizon contracts inward at a pace that gradually erases distant galaxies from our future. The speed of light caps how fast we can move and how fast we can communicate. None of these limits was designed. None of them is personal. They are properties of the universe as it actually exists. And yet, within the bounded region they leave us, an enormous amount remains possible. Within the local group alone, there are roughly 7 trillion stars across all the galaxies combined. Within the Milky Way, there are roughly 250 billion stars, and likely more planets than stars. Within our own solar system, there are 8 planets, hundreds of moons, millions of asteroids and comets, and an enormous quantity of raw material from which a civilization could be built. We have not yet visited most of our own solar system. We have not yet set foot on any planet other than Earth, and any moon other than our own. We have not yet begun, in any serious way, the project of becoming an interstellar species. The walls are real, but we are far from them. We are at the very beginning of the journey. Whatever humanity is going to become within the bounded sphere of our cosmic inheritance, almost all of it is still ahead of us. The question of how far we could spread before the universe stops us is, in one sense, a question about the upper limit, but in another sense, it is a question about how much of that limit we are going to actually approach. We could approach it slowly, taking millions of years to extend ourselves outward. We could approach it not at all, remaining on this single planet until something ends us. We could push toward it aggressively, beginning the great project of cosmic expansion within the next few centuries. The walls will be there regardless. What changes what we control is what we do within them, and there is a kind of quiet dignity in that. The cosmos has given us a finite stage, but it has also given us time. It has given us a planet, a star, a galaxy, a local group. It has given us consciousness, intelligence, the capacity to comprehend our situation. It has given us the ability to do science, to build technology, to dream, to plan, to imagine futures, and then try to realize them. The walls are real. The opportunities are also real. And the proper response to the discovery of cosmic limits is not to give up on the cosmos. It is to engage with it fully, knowing what it is, knowing what it permits, knowing how brief and bounded our window is. We may never reach Andromeda. We may never visit the galaxies of the Virgo supercluster. We will certainly never touch the trillions of galaxies beyond our horizon. But we can reach the next star. We can study the planets we know exist. We can build instruments that see deeper into the universe than any species has ever seen. We can create cultures, philosophies, scientific traditions that explore the bounded inheritance we have been given. We can become, within the cosmic island we share, the most fully realized version of ourselves that we are capable of being. The universe will not stop us from doing that. The walls only close around what lies beyond. Within them, the room is enormous. Within them, the time is vast. Within them, the possibilities, while not unlimited, are far greater than anything any human civilization has yet begun to explore. So if you take one thing away from this exploration, let it be this. The universe is built to keep us small in a certain sense, but it is also built to give us, briefly, an extraordinary stage on which to exist. The walls are real, but they do not press against us yet. They define the maximum size of our future civilization, but they leave us with a sphere so large that humanity has not yet begun to fill even a tiny fraction of it. The cosmos will not let us be everything. It will let us be a great deal. And the difference between a small civilization and the maximum possible civilization that physics permits is going to come down to what we do as a species in the centuries and millennia immediately ahead. Whether we leave Earth, whether we build the technology required to cross between stars, whether we develop the social institutions required to sustain a project across generations, whether we survive long enough to even begin. These are open questions, and the answer to all of them depends, ultimately, on choices that are being made right now by humans alive today, who will shape the conditions that determine what is possible for everyone who comes after. The walls are out there in the deep cosmic future. They are real, and they are absolute. But before we reach them, before we ever encounter the actual limits that the universe imposes, there is so much that could still be done, so much that could still be built, so much that could still be discovered, that the limits feel almost beside the point. They are real. They will eventually matter. But for now, for this generation and the next 1,000 generations, the work is not bounded by the cosmic walls. The work is bounded only by what we are willing to attempt. And that, perhaps, is the most important thing the universe teaches us when we calculate the limits of cosmic expansion. The limits are real, but they are far. The walls are there, but they have not yet closed. The journey toward whatever maximum future humanity can achieve is just beginning. We are not at the end of the story. We are not even in the middle. We are at the opening pages, writing the first chapter of a story whose full length, by cosmic standards, could span billions of years. What we do next matters not because it determines whether we reach infinity, the universe forbids us infinity, but because it determines how much of the finite possibility within our bounded sphere we actually realize. The cosmos gives us a stage. We choose, collectively, how richly to perform on it. The walls give us a deadline. We choose how much we accomplish before that deadline arrives. The cosmological event horizon defines what we can never have. We choose what we will do with what we still can have. And the answer to the question of how far humanity could spread before the universe stops us, in the end, is less interesting than the question of how much humanity will choose to spread while the universe still permits it. The cosmic limits are not the urgent ones. The civilizational limits are. The limits of will, of cooperation, of survival, of imagination. The walls of physics are out there in the deep future, patiently waiting. The walls of choice are right here, right now, defining what every generation will or will not attempt. And the most honest answer to our question is that we do not yet know how far we will spread. We know what physics permits. We do not know what we will achieve. That part of the story is still being written. Look up tonight if the sky is clear. Find a star you do not know the name of. Imagine that on a planet orbiting that star, billions of years from now, a member of our distant descendant civilization is standing under their own night sky, looking back toward our part of the galaxy, trying to understand the history that produced them. Imagine that they are the inheritors of whatever we do in this century, this millennium, this brief window when the choices were still ours. Imagine that they are the proof that humanity reached beyond the cradle, beyond the single fragile planet, into the bounded but vast region of the cosmos that physics permits. They will not have access to the galaxies beyond our local group. Those will be long gone by their time. They will not see the cosmic microwave background. It will have faded beyond detection. They will not be able to verify most of the cosmological history we currently take for granted. They will live in a smaller, simpler observable universe than the one we inhabit now. But they will exist. And their existence will be the answer to the question we have been asking. The universe could not be filled by us. The walls would not allow it. But the walls allowed enough. They allowed a future. They allowed a civilization that spread beyond Earth, that crossed the gap between stars, that established itself in many worlds, that survived through the merger of the Milky Way and Andromeda, that endured into eras whose names we have not yet invented. The walls allowed a great deal. They only forbade everything. And everything was never going to be ours anyway. No civilization, in any universe, in any era, was ever going to be allowed everything. The cosmos does not work that way. But the part that the cosmos does allow, the part within the walls, is more than enough for a species to spend billions of years exploring. We have been granted a bounded inheritance. The size of it is staggering by every human measure. The question now is whether we will rise to meet what physics permits, or whether we will fall short of it, ending our story before we ever began to approach the limits that the universe set for us. The answer is up to us. The walls are not closing fast. The cosmic deadlines are not pressing. We have time, we have stars, we have a future, if we choose to claim it. And in that choosing, in that act of looking at the limits and deciding to fill as much of the bounded region as we possibly can, we become the kind of species that the cosmos quietly, neutrally, indifferently permits. Not the masters of the universe, never that, but the inhabitants of one bounded island within it, the conscious witnesses to one particular bounded slice of cosmic time. The brief flowering of intelligence that, for however long it lasts, makes the inside of the walls into something more than empty space. That is the most that physics permits. That is also perhaps more than enough. If you enjoyed this deep exploration of the cosmic limits that constrain humanity's future, please like this video and subscribe to Hidden Beyond Stars. Tell us in the comments what surprised you most about the size of the reachable universe and what we should explore next. These are not just questions for scientists. They are questions for all of us, because the future that physics permits is the future that we, collectively, get to choose how to fill. Thank you for spending this time with us. We will see you in the next journey.